Dear students, today we are going to see the topic oscillators. What is oscillator? Oscillator is a circuit which produces output without having any input signal. This is a major difference between amplifier and oscillator. If any circuit, if it acts as an oscillator, it should be satisfied minimum two conditions. That condition is known as a Bargasan's criterion. So the condition for the oscillation is, the first condition is the total phase shift around the loop is 0 degree or 360 degree. That is the first condition of oscillator. And second one, the loop gain of an oscillator beta A should be 1 unity. So if circuit which satisfies these two conditions, then only it acts as an oscillator. So oscillator is one of the example of positive feedback concept. Actually, the feedback, we have two types of feedback. One is a negative feedback, the other one is a positive feedback. So normally all amplifiers are utilize a negative feedback, but the oscillators utilize positive feedback. So the open loop gain of positive feedback is AF. That is a gain with the feedback, which is equal to A divided by 1 minus beta A, where here the beta A is a gain of oscillator. As I said earlier, the one of the condition for oscillation, that is a Bargasan's criterion, is beta A should be 1. So when you put 1 here, your oscillator closed loop gain becomes infinity. That means without any input signal, because the gain is output by input, so V0 by Vi. So without any input signal, when the Vi is 0, then only it becomes infinity. So without giving any input, the circuit itself generates output. That is a concept of oscillator. Now we are going to see the types of oscillator. What are the types in oscillator? Generally, the oscillators are broadly classified into two types. One is a sinusoidal oscillator, other one is a non-sinusoidal oscillator. Sinusoidal oscillator is based on the waveform which the oscillator is going to generate. Based on that, we can have two major broad classification. Sinusoidal oscillator is an oscillator which is going to generate sine wave as an output. Non-sinusoidal, other than sine wave, if the oscillator generates square wave, triangular, rectangular, those are coming under non-sinusoidal oscillator. So under the sinusoidal is further classified into three. One is a LC oscillator, and second one is a RC oscillator, and last one is a crystal oscillator. LC, inductor and capacitor, that will play a vital role. The key elements of LC oscillator is L and C, and the key elements, heart of the RC oscillator is a resistor and capacitor, RC, and the final one, crystal. Here the crystal will play a vital role, that is the heart of the crystal oscillator. So here in LC is otherwise known as a high frequency oscillator or RF oscillator, high frequency oscillator or RF oscillator, and RC oscillators are otherwise known as low frequency oscillator or audio frequency oscillator, AF. Here is RF, radio frequency, and RC is a audio frequency, AF oscillator. If you want to generate highly stable output, that could be possible only with the use of crystal oscillator. Here the crystal is made up of silica, because since it is very cheaper, easily available, so your one of the key ingredients of the crystal is silica. So these are all the major classifications of sinusoidal oscillator. And the second one, non-sinusoidal oscillator. So example of a non-sinusoidal oscillator is, one of the major example is multivibrators. multi-vibrators. It is a circuit which is going to generate the waveform other than sine, square wave, pulse, train of pulses. So this rectangular waveform could be possible with the use of multi-vibrators. Now, this class we are going to concentrate only sinusoidal. Under the sinusoidal, we start with LC oscillator. Thank you. Okay, today we'll see LC oscillators. As I said earlier, the last class, the key elements of LC is inductor and capacitor. So the basic principle of oscillation of LC oscillator is interchange of energy between L and C. We know the basic property of the inductor and capacitor. Whenever we apply the voltage across the capacitor, it stores the charges in electric field. That is a property of both are energy storage device. So when we apply the voltage across the capacitor start charging and it stored the charges in electric field. The same thing in inductor. Inductor also is a reactive element, is that also used for energy storage device. Whenever the current flows through the inductor, it stores the energy in magnetic field because the field around the coil starts generates. So that means the energy will be stored in magnetic field. So the basic principle of oscillation of LC oscillator is the interchange of energy between electric field and magnetic field will lead or will generate oscillation. So how the interchange of energy between the capacitor and inductor happens, that we will see now. Let us consider the parallel L and C. Now the capacitor is connected across the external battery. So here you have the switch, that is S1, and here the switch is S2 and this switch is S1. We have two switches in this LC tank circuit. That LC parallel LC circuit is known as a tank circuit. Now the switch S1 is closed initially. Now the S2 is open. So when the switch is closed, the battery is directly connected across the capacitor. Now the capacitor starts charging towards the maximum value of this battery. Let's see. Let's consider the battery voltage is 5. The maximum voltage stored across the capacitor is 5. If it is 10 volt. Once the capacitor is fully charged, that S1 is open. So initially, now entire charge will be in electric field. That means across the capacitor. So the upper plate is plus and the lower plate is minus based on the polarity of the battery. Now we are going to close the switch S2. Once the S2 is closed, the capacitor start discharging through the coil. The electrons will be flowing from lower plate to upper plate. That is upper plate number is 1, lower plate number is 2. You take from 2 to 1, the electrons will be moving. The conventional direction will be in the opposite way. That is a 1 to 2. So upper plate to lower plate. So now the electrons will be moving towards the coil. When the electron flows, the current will be flowing through the coil. Once the current starts flowing through the inductor, so field will be generated across the inductor. Slowly, that magnetic field keeps on increasing. Once the capacitor is fully discharged, the entire charge will be transferred to the magnetic field. That means around the inductor or around the coil. That means the entire electric field energy is converted into magnetic field energy. Once the capacitor is fully discharged, that is the maximum amount of energy occurs or appears across the inductor. According to the Lenz's law, once your inductor is fully field is fully generates, the current flows stops. Automatically, the field around the coil starts collapsing. According to the Lenz's law, that keeps that current, electron movement in the same direction. That means from lower plate to upper plate. That the field will release the electrons that will be accumulated on the plate 1, upper plate. So after that means the energy from the magnetic field is slowly converting back to the electric field across the capacitor. Once the charges magnetic field is totally collapsed, that means the entire energy is converted back to the electric field energy with opposite polarity. That means the upper plate becomes negative and lower plate becomes positive. So we will get the diagram like this. Upper plate is negative and the lower plate is positive. That is the two becomes positive and one becomes negative. Now the electric energy is fully across the capacitor. That means the energy is in electric field. Now the magnetic field energy is converted to electric field. The same process repeats again and again. Again, your capacitor start discharging through the coil in the opposite direction. Now the upper plate is negative. So from this to upper plate to lower plate, the electrons will be moving. The conventional direction of the current is in opposite. Once the current flows through the inductor, again the field will generate. Is slowly increasing across the around the coil. Once the capacitor is fully discharged, your field around the coil is maximum, but in opposite direction. Here is upper and down, here is down and upper. That means the entire energy will be in magnetic field. Around the field, once the current flow stops, the field around the coil starts collapsing. It keeps the electron flows in the same direction. Again, the lower plate becomes negative and upper plate becomes positive. The same diagram will repeat. This process repeat again and again. This interchange of energy between electric field and magnetic field will generate oscillation. That is the basic principle of oscillation of LC oscillator. Good morning, students. We move on to the next topic. Last session, we have seen the basic principle of oscillation of LC oscillator. How the LC tank circuit generates oscillation. Now, we are going to see the classifications of LC. I said earlier that LC will have a further three classification. One is a Hartley oscillator. Second one, Colpitts oscillator. And third one, Clap oscillator. There are three types of LC oscillator. What is the difference? Based on because that all three oscillators working is same. The only the difference is construction. That is a tank circuit, feedback network. Because this as I said earlier, the oscillators utilizes positive feedback. If any feedback amplifier, we have two blocks are very important. One is a open loop amplifier A, and second one feedback network beta. The output of without any feedback network, when you give the input, you will get the output. That is an open loop amplifier. That gain is open loop gain. In order to increase the stability or increase the gain, we need to go for feedback amplifier. If you want to increase the stability, we apply negative feedback concept. If you want to increase the gain, we have to apply positive feedback concept. Now, here the output of this feedback open loop will be given back to your feedback network. From the feedback network, the signal will be given back to the input. Based on this feedback signal with the input signal, if both are in phase, feedback signal is in phase with the input signal, then it is known as positive feedback. As a result of this, your gain will be increased. That is one of the advantage of positive feedback. If your feedback network is out of phase with the input signal, then it is negative feedback. Out of phase, then it is negative feedback. Now we are discussing only the positive feedback application, oscillators. So in all three oscillator, only the feedback network will be different. How we are going to construct this feedback network? Based on that only we can have three different classification, and based on that each oscillator will have a unique frequency of oscillation and condition for oscillation. Let's start from Hartley oscillator. Okay. So Hartley oscillator. Hartley oscillator. Its feedback network. So Hartley oscillator, we have the amplifier, common emitter amplifier circuit. RFC, radio frequency choke, and R1, R2 is a biasing resistor, and RE and CE is a emitter resistor and bypass capacitor. Output will be taken from the collector, and input will be given to the base of common emitter amplifier. This is a normal common emitter amplifier. Now we are going to convert this open loop amplifier into feedback, positive feedback. It's a Hartley oscillator. So we have to include the feedback network here. So in Hartley, the feedback network is made up of 2 inductor and 1 capacitor, and the center tape inductor. The midpoint should be grounded. That means both the end of the inductor will maintain opposite phase. Both will have 180-degree phase shift. So the output of the common emitter will be given to the feedback network. Then output of the feedback network will be given back to the input of common emitter amplifier. That is the entire construction of Hartley oscillator. Here we have L1 and L2, only one capacitor we have C. Now we see this is the entire construction of Hartley. Now we'll see the working of Hartley. When the supply is given, the current will be flowing. So here instead of RC we are using RFC, radio frequency choke. The coil will be used that blocks the AC transient from the power supply. It allows only the DC signal to the collector. Now which is coupled to the tank circuit through the coupling capacitor CC. Once the voltage reaches the tank, we already discussed the basic principle of oscillation of tank circuit, that is a LC oscillator, interchange of energy between the capacitor and inductor. So that process will start at the tank circuit. Here we have L1, L2 and one capacitor. So the output of the amplifier will be appeared across your L2, and whatever the voltage across this L1, that acts as a feedback signal VF, that will be given back to the input of common emitter amplifier. That process will repeat again and again, because I already explained the basic condition for oscillation. One is a total phase shift around the loop is 0 degree or 360 degree. That is the first condition. So in this circuit, here we are using common emitter amplifier. That common emitter amplifier will provide 180 degree phase shift, and another 180 will be introduced from the tank circuit, because both the end of this tank circuit will maintain opposite phase. So this will introduce 180 degree phase shift. So the total phase shift around the loop is 0 degree or 360 degree. And second one, the loop gain beta A should be 1. That is the second condition for oscillation, Barghasen's criterion. So this feedback process will repeat again and again till it reaches beta A equal to 1. So here we all raise one question, that is why we should maintain beta A is 1, because there are two kind of oscillations in oscillator. One is a damped oscillation, other one is a undamped oscillation. Damped oscillation is nothing but the output signal, the amplitude of magnitude of the output will reduce with respect to time. So it keeps on decreasing with the time. That means, so you will get the waveform like this. Initially, it will maintain the constant magnitude and it keeps on decreasing with the time. That type of oscillation is a damped oscillation. So whatever the circuit which will not maintain that beta A is 1, that means beta A is less than 1, if any circuit, which produces this damped oscillation. But our aim is we need to produce undamped or sustained, both are same, sustained oscillation. Our aim is to generate sustained. The sustained is nothing but the output magnitude is constant with respect to time. There is no more changes on the magnitude. So this could be possible with the condition is beta A is equal to 1 or greater than 1, greater than or equal to 1. You are when the circuit satisfies this condition, then only we can reach this undamped oscillation. So till we reach that undamped oscillation, this feedback process will repeat again and again till the circuit reaches beta A equal to 1. Once it reaches, we will get the undamped oscillation or sustained oscillation. That is a working of Hartley oscillation. Now the frequency of oscillation. Now we'll see the frequency of oscillation of Hartley oscillator. In Hartley oscillator, we have two inductor L1 and L2 and one capacitor. So we know the frequency of oscillation of tank circuit. F is equal to 1 by 2 pi root LC. That is the general frequency of oscillation of tank circuit. Since we have two inductors, both are in series, your frequency of oscillation of Hartley oscillator is 1 by 2 pi square root of L equivalent into C. That L equivalent is where the L equivalent is L1 plus L2. Here we have to include one more term as a 2M. That M is a mutual inductance between the coil. Since it is very small, most of the practical cases this will be neglected. But even though the ideal case, it should be included in this L equivalent calculation. So L equivalent is equal to L1 plus L2 plus 2M. So that is the final frequency of oscillation of Hartley oscillator. Thank you. Good morning, students. Now we are going to see the second classification of LC oscillator, that is a Colpitts oscillator. The major difference between Hartley and Colpitts is in feedback network only. In Hartley oscillator, we are using two inductor and one capacitor connected in parallel that acts as a tank circuit of Hartley oscillator. But in Colpitts, we are using two capacitor and one inductor. Both are connected in parallel. That acts as a tank circuit of Colpitts oscillator. There is a major difference between Hartley and Colpitts. In Hartley, we are using tapped inductance. In Colpitts, we are using tapped capacitance. There is a major difference. So now we will see the circuit diagram for Colpitts oscillator. Open loop amplifier common emitter. That will be same for both the oscillator circuit. Here in collector we are using RFC same, and R1 and R2 is a biasing resistor, and the emitter we have RE emitter resistor and bypass capacitor CE. Here we have two capacitor, one is at the collector and other one is at the base. Both are known as a coupling capacitor. That is the open loop common emitter amplifier. Now we have the feedback network. So as I said earlier, the major difference between the Hartley and Colpitts is only in the feedback network. So instead of using two inductor, in Colpitts we are using two capacitor, and this capacitor is connected in parallel with inductor. And here we use tapped capacitance. So the midpoint should be grounded. Here is C1 and this one is C2 and here is inductor L. This acts as a feedback network of Colpitts oscillator. The output of the common emitter will be given to the input of feedback network from the feedback network, the feedback signal is given back to the input of common emitter amplifier. So the output will be appeared across C2, that is P0 will be here, and the feedback signal will be appeared across C1, that is BF will be in C1, across C1. So this BF will be given back to the input of common emitter. The remaining working is same. When the supply is given, the RFC will be active, so that will block the transient AC from supply. So only it allows only the DC voltage to the collector, so which is coupled to the tank circuit. Once the voltage reaches the tank circuit starts its operation. That means the charging and discharging action will start. That will happen in tank circuit. The capacitor starts charging towards the maximum value. Once the capacitor is fully charged, it starts discharging through the coil. So electric field energy is totally converted into magnetic field energy. So this interchange of energy between capacitor and inductor will produce oscillation. That will be given back to the input of common emitter amplifier through the coupling capacitor CC. This process will repeat again and again, because whatever the oscillation generates from the tank circuit is the initial excitation of the oscillation. So that will be given to the input of common emitter, which is amplified by this amplifier. The amplified version will be appeared at the collector, and this will be given back to the tank circuit. This process will repeat again and again until the entire circuit reaches beta A equal to 1, until we get sustained oscillation or undamped oscillation. Second point, how the circuit gives 0 degree or 360 degree. That is another condition for oscillation, Bergesen's criterion. Here, one is a common emitter, that will be same as a Hartley oscillator. This will introduce 180 degree phase shift. The another 180 will be introduced by this tank circuit, because since it is a center tape, both the end of the tank will maintain the opposite phase, and this tank circuit will introduce another 180. The total phase shift around the loop is 0 degree or 360 degree. That is a second condition for oscillation. So now the frequency of oscillation of this Hartley oscillator is here. We know the frequency of oscillation of the tank circuit. That also similar to Hartley, that F is equal to 1 by 2 pi root LC. Since we are using two capacitor in series, that frequency of oscillation is equal to 1 by 2 pi root L into C equivalent, where C equivalent is equal to 1 by C1 plus 1 by C2. That means 1 by C equivalent is equal to 1 by C1 plus 1 by C2. That is your that is the equivalent C equivalent formula. Because since it is a series, we apply the parallel combination formula, the two capacitors are in series. So the equivalent is 1 by C equivalent is 1 by C1 plus 1 by C2. That is a entire frequency of oscillation formula for Colpitz's oscillator. And the condition for oscillation for Colpitz's oscillator is HFE gain is equal to C2 by C1. But in Hartley oscillator, the condition is HFE equal to L1 by L2. That is a condition for oscillation for Hartley, and this one is a condition for oscillation for Colpitz's oscillator. So this is a second classification of LC oscillator. Thank you. Good morning, students. Now we are going to see the third classification of LC, that is clap oscillator. This clap is an improved version of Colpitz's oscillator. We have discussed the Colpitz's oscillator working and construction. So the construction of the Colpitz is, in the feedback network, we have two capacitor and one inductor. That is a Colpitz's oscillator tank circuit, and here midpoint is grounded. Here is C1 and C2. when we go for the clap oscillator, we are going to include one more capacitor that should be connected in series with the inductor, LC3. The purpose of adding this capacitor is to improve the frequency stability. If you want to improve the frequency stability of Colpitts oscillator, we have to include one more capacitor in series with this inductor. That resultant circuit is known as a clap oscillator. The remaining entire part of the construction will be similar to Colpitts. Here you have open common emitter amplifier, RFC, and R1 and R2 is a biasing resistor, and here is RFC, radio frequency choke, and RE emitter and bypass capacitor, and output will be given to the feedback network, and from the feedback network, the feedback signal will be given back to the common emitter amplifier. That is the entire circuit diagram for clap oscillator. Remaining working, everything will be similar. Now the supply is given, it blocks the AC, it allows only the DC. That will reach the tank circuit. Once the signal reaches the tank circuit operation starts. The charging capacitor start charging towards the maximum value. Once it charges, it start discharging through the coil. That interchange of energy will happen. That will produce the initial excitation of the oscillation. That will be given to the common emitter, which is amplified by the common emitter amplifier. The amplified version will be appeared at the collector, and that will be given back to the tank circuit. That process will repeat again and again till the entire circuit reaches beta A equal to 1. That's the first point. Second one, your common emitter will introduce 180. The another 180 will be introduced by the tank circuit. The total phase shift around the loop is 0 degree or 360 degree. Here, the frequency of oscillation F is equal to 1 by 2 pi root L into C equivalent. But here, 1 by C equivalent is equal to, we have a 3 capacitor, 1 by C1 plus 1 by C2 plus 1 by C3. But the frequency condition for oscillation will be similar to Colpitts oscillator. There is no more changes on the condition for oscillation. Only the purpose is, it is going to improve the stability. So HFE equal to C2 by C1. That is the condition for oscillation of clap oscillator. Thank you.